Hyperbolic and Parabolic Unimodular maps. Please.
Thank you. Yeah, no. You got it off. So now it's on. Yeah. The light is on, so I guess it's on. Yes, so I would like to reiterate, to begin with, some of what Luigi said about thanking the organizers. Indeed, this is a wonderful program. It's been very nice being here and this week as well. And I may as well reiterate, there is indeed the PIM Summer School in Montreal, which does look like it's going to be very nice, and I'm certain that Luigi's sister is very talented, though I don't have personal knowledge of that. But let's leave that for a while. Indeed, I'm going to talk about some joint works with my co-authors, Tom Hutchcraft, Asaf Nachmias, and Gurab Ray, who you see on the bottom here. Gurab got married recently. This is from his wedding. So, and then now there's some people commented there's no picture of me, but I figure you can see me, so so there's no need. This is actually an unusual occasion, since the other co-authors are all here in the room, so you could also see them. Gurab was at UBC and is now at here at Cambridge. Tom was at Cambridge, is now at UBC, so we did sort of a trade-in, and Asaf is now in Tel Aviv. So, okay, so there are several words in the title: hyperbolic, parabolic, unimodular, and maps. Some of these things we've seen already, and some not so much. And I'll start by talking a bit about what unimodularity means, since many people are not familiar with that. And this goes back to the notion of Benjamini-Schramm limits. Well, there are several other approaches to unimodularity. This is a picture of Itai and Oded from roughly the right period. If you look closely, where is the pointer here? Yes, if you look closely here, you can see a little bit of Gil Kalai also. But sorry, Gil. So what is a Benjamini-Schramm limit? The idea of a Benjamini-Schramm limit is that we have some graph and we want to study the structure of the graph near a typical vertex. So if we have some graph, G, okay, so we have the Benjamini-Schramm topology. As we say that the sequence of graphs converges if the balls around any given radius converge. So we say that Gn with a root rho, so rho is a marked vertex in the graph, so that's a root. So yeah, I should maybe say, so I am also following an old tradition from when slides were actually little pieces of paper that sometimes they get lost and mismanaged. So there should have been another slide with these things here. But yeah, so if you have a graph, I inserted this picture and it seems to have overwritten the definition. So we say that a sequence of graphs Gn converge to an infinite graph G rho. So this means that the ball of radius, the ball in Gn of radius r around the root rho converges to the ball in G of radius r, also around the respective root rho. And if you have a finite graph, you can just consider it as a random graph by taking a root uniformly at random. So now we have a finite graph G, we take a root uniformly, and now this is a random rooted graph, since the root is random, and we can consider its limit under this topology. So the limit in general will be a random infinite graph. So I'm sure many of you are familiar with those things, so there's a bunch of exercises here. Now, given the time allotted, I will not go through all of them, but we could go through a couple of them. So maybe start with the torus, which is the easiest one. So if you have the torus, say an n by n two-dimensional torus where the two sides are connected, it doesn't really matter where you put the root rho, you have the same graph. And if you look at the ball of radius r, if the torus is large enough, it looks the same as the ball of radius r in the infinite lattice. So the torus converges to the infinite lattice ZD, and the cube also converges to the infinite lattice ZD because the root is random. So if you now have a finite cube, with high probability the root is not going to be near the edges, and so with high probability you just see something that looks like part of an infinite lattice for any fixed radius r. Again, the crucial thing is that you only look at any fixed radius r, so r is arbitrary but finite. I don't know, so any particular requests for some of the others that I should discuss? So we could put this to a vote. No.
Sizen and genus theta.
Yes. So that's a tricky one. That's the one exercise in this list that is actually an open problem. So if you take the uniform planar graph of size n, then this is something that's come up in several of the talks this week, and this converges to a uniform infinite planar map. In the case of triangulations, you get the UAPT. For quadrangulations, the UAPQ, and there are several variations. If you take
graph instead of map?
If you take
Graph, planar graph?
planar graph. Well, okay, so for planar graph, there is a notion of embedding and connectivity. So for connected graphs, the answer should be yes. I'm not sure if it's been done. There are some better experts on exactly which classes of maps this has been done for. But yeah, so it should be the case for planar graphs as well. Yeah, so one more maybe worth mentioning is, or a couple of comments. So the random d-regular graph, so if you take a finite d-regular graph, this converges to the random d-regular tree. And so locally you don't see any cycles. So you will have some cycles in the graph and even some small cycles, but if you take a typical vertex, you do not see them within finite radius of the circle. Finite Cayley graphs are also interesting. They converge to a Cayley graph of some limit of the groups. So that's another interesting example. And one important property of Benjamini-Schramm limits, so there are many examples of graphs that are known to be Benjamini-Schramm limits, some that are conjectured, and every Benjamini-Schramm limit has a property that we call unimodularity. And this is defined in terms of a mass transport principle that's on the board, that's on the projector now. And what it says is the following. So suppose we have some function f, which takes as input a graph and two marked vertices on the graph, and just a real function, say it's positive function, so that there's no problem with the existence of the expectation. So we have some function of f of g and 2 points, and you should think of this function, g of f of g x y is the amount of mass that x sends to y. A vertex x sends to vertex y some amount of mass. And what we want is that if you take some random graph, so now we have some random graph g and rho, and we look at the total amount that rho sends to every other vertex. So we sum f of g rho x over all x, that's the total amount that rho sends to every other vertex in the graph. We look at the expectation of that. It's expectation because the graph is random. The function is just given by the graph and the 2 points, but the graph itself is random. So we take expectation. This should be the same as the expectation of the total mass that the root rho receives from all of the graph. So that's the sum of f of g x rho over all x. So the intuition is that whenever you have such a rule for transporting mass in the graph between vertices, the expected mass going out is equal to the expected mass going in. So what's some simple examples of this? So maybe a very simple example is that every vertex sends 1 unit of mass to every neighbor. So the amount of mass that the vertex sends out is the degree, since you send 1 to each neighbor. The amount of mass that the vertex receives is also the degree. because you receive 1 from each neighbor. So this is not very interesting. This is satisfied for this function, you get equality for any graph without expectation even. But here's a slightly more interesting example. Suppose every vertex sends 1 unit of mass to every neighbor if the neighbor has degree 17. Otherwise not. So the amount of mass that you send out is now not a degree, it's actually the expected number of neighbors of degree 17. What's the amount of mass that you receive? Well, if you don't have degree 17, you receive nothing. If your degree is 17, then you receive 1 from each neighbor. So what this gets is that the expected number of neighbors with degree 17 is equal to 17 times the probability that the degree of the root is 17. So that's what the mass transport gives us here. So that's already something not completely obvious. But this again holds for many graphs, and the mass transport principle says that for any function this is satisfied. So are there any questions? I should, again, taking a note from Luigi, if anything is not clear, please do interrupt me. And if there are any questions about the mass transport principle, we will see a couple more examples later. But so this is an extremely powerful method. It's been used in many settings, including percolation theory for very interesting applications. And one of the notes about the mass transport principle is that in many cases, the trick to proving something is finding the correct mass transport. So you need to sort of understand what is the thing that you are looking for, and say if you're looking for vertices of degree 17, you might do something like that. And you need to tailor a mass transport to that, and once you apply it, you get something interesting from the mass transport principle. So there is one question that should be mentioned here. So we said that every graph that is a local limit, a Benjamini-Schramm limit of finite graphs, is necessarily unimodular. And here's a question, and I'll write it in big because it's a big question. So is every unimodular graph a Benjamini-Schramm limit? And we'll put a big question mark. And again, that's a big question, so there were various attempts to prove it, but it's still open. And even in the case of groups, this is a particularly interesting question, since it's relatively easy to show that every group, if you have a group and you have a Cayley graph with some arbitrary generators, then this is unimodular. But it's not known whether every group is a local limit of finite groups. And if this is the case, this would have a number of interesting applications in group theory. So again, a big question for any of the aspiring students here. Okay, so we talked about unimodular graphs, and I want to say a bit about hyperbolic and parabolic graphs now. So the graphs we see here, so these are actually circle packings of graphs. So we have here 3 triangular lattices, three triangulations. You have a small one. You only see half of the one on the left. This is the 5 regular triangulation. So the decahedron, or is this a icosahedron? I always confuse them. Icosahedron, I think. Yes. So. But there's the map, there's the dual. We'll have a lot of chances to get confused later between maps and their duals. So this is maybe just important. So you have this one, which is a finite one. In the background, you have the 6 regular triangulation. Again, you may recognize this picture from a substock. And in the background, you have the 6 regular triangulation, which is embedded, drawn using a circle packing. So every vertex is a circle, and the tangency graph is that of the 6 regular triangulation, just the regular triangular lattice. And on the right, you have the 7 regular triangulation, again drawn using a circle packing. So this one, so in the case of the left one, you only see half of it because it's drawn on the sphere and half of it is hidden. In the case of the 6 regular one, we only see a small part of it because it's drawn in the infinite plane. And in the case of the 7 regular one, you actually see all of it. It's drawn in the hyperbolic plane. And there's a question, so what is the difference between them? So just thinking of a triangulation, why is the 6 regular triangulation so different from the 7 regular triangulation? So, so there are many properties that distinguish them. We will see some of them. But again, these graphs being Cayley graphs or transitive, these are unimodular. There are many other graphs that are unimodular. So as I said, any Cayley graph is unimodular. The UAPT and its variations, other uniform infinite planar maps, are all unimodular since they are defined as local limits, as Benjamin-Schramm limits of finite maps. You have the stochastic hyperbolic triangulation that Curien constructed, which is a hyperbolic version of the UAPT. So the picture on the right here is not quite of that, but this is due to Curien. I believe it's not of that, right? Yes. The picture on the left and right are actually a different map, which is also unimodular. So this is the Poisson-Voronoi or Poisson-Delaunay map. So you start with the Poisson process on the plane or on the hyperbolic plane. And once you have this, you have a Delaunay triangulation corresponding to it. So this is a canonical way of coming up with a triangulation for many point process, where the triangles correspond to circles through 3 points with no other points in the interior. And you can do this in the hyperbolic plane or in the Euclidean plane. You get again you get unimodular maps, and it's not hard to show that these are also unimodular. They are in fact also limits of finite graphs. So, and again, there's a question of what is the distinction between them. Yeah, so as I said, the right one is due to Curien, the left one is due to Google. So this is the main theorem that I'm going to talk about. And you've seen aspects of this theorem in the last 2 slides, and let me also put the theorem on the board. Since this is really the main outcome of this talk, so if you have any unimodular map, then it's either parabolic or hyperbolic. So we have this dichotomy where maps are split into 2 types. And what do we mean by this? Well, there's quite a large number of different properties of the map that characterize this. You can see a few of them there. So this is actually a picture from one current version of the paper. And so someone complained, was it James? Yeah, that someone complained that it's unlucky to have 13 clauses, and so we split out this thing about the dual of the map into a separate one, but somehow we shuffled things around and there are still 13. So, but let's just go back to this, which is maybe easier on the eyes and on the brain. So what are some of these properties? And again, many of these properties are things that have been known to distinguish between hyperbolic settings and parabolic settings, and are known notions of hyperbolicity that people have looked at before. But what this theorem says is that in the context of unimodular maps, they are all equivalent. So what do we have? We have a curvature, which I will discuss a bit later, but roughly the hyperbolic case, you have negative curvature, and in the parabolic case, you have zero curvature. You have properties of amenability and expansion. So if you look at the 7 regular triangulation, so this is an expander. Every set has a boundary comparable to the set. Whereas in the 6 regular one, it is not. In the 6 regular one, if you take a large ball, the boundary is roughly the square root of the area. So you have boundaries which are much smaller in the parabolic case. In the background, the hyperbolic one, you do not. We have the question of the study of spaces of harmonic functions. So we have the Liouville property that every harmonic function is bounded. Every bounded harmonic function is constant. So in the parabolic cases, we have this property. In the hyperbolic cases, we have bounded harmonic functions that are not constant. So in this case, for example, you might consider a random walk, and it converges to some point on the boundary, and you might consider the probability that it converges to the right half, which gives you a bounded harmonic function. You have a Dirichlet function. So these are functions with harmonic functions with finite Dirichlet energy. Dirichlet energy being the sum over the edges of the gradient squared. So do you have a non-constant harmonic function with finite Dirichlet energy? In the hyperbolic case, you do. In the parabolic case, you do not. There are questions of percolation. For percolation, if you take bond percolation or side percolation, you have a critical parameter above which you have an infinite component, that's PC, and you have a second critical parameter above which you have a unique infinite component, which is called PU. And in the parabolic case, they are equal. In the hyperbolic case, they are non-equal. So a conjecture is that if you have any transitive non-amenable graph, then you have a gap between them. So that's one of the nice conjectures in percolation theory. So in the case of unimodular planar maps, this is indeed true. You have the notion of spanning forest. So if you came to a SAFS talk, so that's most of you, you heard a lot about spanning forests, and this will show up also later in my talk. So you have the wired and the free uniform spanning forests. Are they the same or are they different? You have minimal spanning forests. If you assign the edges random weights, and again you can ask, you can look at the wired and free versions of the minimal spanning forests. You have circle packing. So this is what's exactly in this picture. So if you have a graph, you can embed it using a circle packing in the plane. And there are two possibilities. Either you have a circle packing that is locally finite in the entire plane, and as in the case of the 6 regular lattice, or you have a circle packing that has accumulation points on the boundary of a disk, which is the hyperbolic case. So again, this is equivalent for unimodular maps. This is equivalent to all of these other properties. Without unimodularity, some of these connections may break. There's the conformal type, which I will maybe discuss a bit later. And there's finally the question of random walk. So recurrence and transience, which is maybe the most natural dichotomy for random walk, is actually not equivalent. So it is possible to have a transient parabolic map. However, there are various properties of random walks that are equivalent. So the intersection property is equivalent. So if you have two random walks, do the traces intersect almost surely? So this is equivalent. If you restrict to a subgraph of bounded degrees, then it's also equivalent to recurrence. So that's quite a long list, and that's an even longer list. This is a nice circle packing, which it's a nice picture, so I didn't really want to take it out of my slides, although it doesn't really fit at this point. But again, this is so this circle packing is approximately a circle packing of the stochastic hyperbolic triangulation up to a sampling error. And as you can see, it is hyperbolic. It has accumulation points on the boundary if you have very good eyes. And so this is another example of the hyperbolic case. So okay, so I've said quite a lot of things, and we have these 13 clauses that plus the one about the dual map, which can be a bit confusing. So there's another map to help you navigate this paper or this talk. So what do we have here? We see here some of the properties that we have discussed already, and some of the implications between them. So the red arrows are things that are in the new work that I'm talking about today. The black arrows are things that have been known before. So the connection between being a Benjamini-Schramm limit of planar maps and being, so this stands for vertex extremal length. So this is something that was central to Itai Nuded's early work on Benjamini-Schramm limits. You can relate this to notions of amenability. You have the wired uniform spanning forest and free uniform spanning forest, which we will discuss in some great depth. BLPS, as you may recall from Asaf's talk, stands for Benjamini Lyons Perez Schramm, an important paper in this result. Another implication here in the work of Benjamini, Kurien, and Georgakopoulos, who's not here today, but. So again, some of the connections between percolation and the minimal spanning forests are older, but the connection to average curvature is new. And okay, and for the rest of the talk, I'm going to focus about some of these implications. We're not going to cover all of them, unless there are lots of questions. But are there any questions at this point, maybe, before we dive in? So let me say a bit about average curvature, because curvature is really one of the central things in this picture. So it's not really in the center, it's at the top here, but trust me, it's central. So what is the average curvature in a graph? So what is a curvature in a graph? Well, one way to think of a graph, if you have a planar graph, then you can you can imagine that it's made out of, say, squares or rectangles. Let's say these are squares. If you have a quadrangulation, you just glue the squares along their edges. So if you have two squares, you may glue them like that. And if you have yet another square, you glue it like that, and you create a surface out of this. And the surface that you create in this way, you don't need this, right? Yeah. So if you create a surface in this way, then locally within, and of course, if you don't have squares, if you have triangular faces, you take equilateral triangles. If you have higher order faces, you take equilateral polygons of that size. So this is a way to create a manifold out of a map. And this manifold, so when you have two, so within the face, it's completely flat. And when you take two things and glue them along the edge, it's also completely flat near the edge. But at the corners, if you take, say, three squares, you have three right angles, and you glue them at the corner, then you get some corner, actually, a corner of a cube, which is some form of a positive curvature. So it's positively curved. If you take four squares, it will be flat. If you take more than four, you will have negative curvature. Is there some problem?
Yeah.
Should I start again? So let me start by thanking the organizers. Right. So curvature. Yes. So right. So in this way, we define the notion of curvature at a map by looking at the corners. So if you take this, if you glue this. These surfaces, then as I said, it's completely flat except at the corners, and at the corners you may have some curvature. So the way we define it is just by looking at the total angle. So you pretend that each face is a regular polygon. So the angle at the corner of a polygon, if you have a face of degree df, then the angle at each vertex, the internal angle, is df minus 2 over df times pi. So you just look at the total around the vertex. If this is equal to 2 pi, then things are exactly flat there. If it's not equal to 2 pi, then you have some excess and or deficit, and the deficit is the curvature. So if you are less than 2 pi, you have some positive curvature. If you are more, then you have negative curvature. So in the case of triangulations, and you could just think for all of this talk about just triangulations. So in the case of triangulations, this is proportional to 6 minus the degree. So that in the 7 regular one, we have negative curvature, and in the 6 regular one, we have 0 curvature. So we have the curvature at a vertex. If we have a random graph with a root rho, then we just look at the expected curvature. So this is the average curvature. And so, okay, so in the case of the triangulation, as we said, it's just proportional to 6 minus the degree. There's an easy computation just by summing all of the angles everywhere, that if you have any finite map on the sphere, then the total curvature is 4 pi. And this will give us the first implication up here, going from being a Benjaminish Ram limit of planar maps to having average curvature 0. And I should emphasize at this point that we are talking that the property on the left here is not the property that the graph is a Benjaminish Ram limit of some finite graphs, but it's a Benjaminish Ram limit of planar graphs. And this is not equivalent. As an example, if you have the D regular tree, so the D regular tree is a Benjaminish Ram limit. It's the Benjaminish Ram limit of the finite D regular graph, but it's not a Benjaminish Ram limit of planar graphs. And we can even see this from this curvature argument. So the D regular tree. So in the tree, you can see in the tree you have faces which have infinite degree, and this fits just as in exactly the same way into this formula. And you find that in a tree, in the D regular tree, you have negative curvature everywhere. So how do we deduce? So as I said, Euler's formula gives us that the total curvature on a finite map on the sphere, so on any finite planar graph, the total curvature is 4 pi. So if you take a random vertex, the average curvature there is 4 pi over this number of vertices. So if the number of vertices goes to infinity, this goes to 0. And that's at the heart of this connection, that if the graph is a Benjaminish Ram limit of planar graphs, then it has average curvature 0. So let's move on. So we have average curvature 0, and I want to deduce from this some things about either the conformal type or the spanning forest. So
Can you just clarify? So this question that you have on the board here?
Yes, that one.
So how does that fit into your picture? So unimodular maps are not known to be equivalent to any of these boxes?
So that's actually another result in paper, that unimodular maps are always Benjaminish Ram limits of finite graphs. So it's not on this slide, and it's not on any of the slides, but a unimodular planar map is a Benjaminish Ram limit. So there are other unimodular graphs that are not planar. And for those, it's not known whether they are Benjaminish Ram limits. So this question is not in the context of planar maps. This is in the context of planar maps, we actually know the answer is yes.
Oh, got it. So everything here is in the context of planar maps.
Yes, this whole talk is in 2 dimensions.
Right, okay.
So, okay, so we have here some things about the conformal type which we could discuss at this point, or we could go and talk about the spanning forests. Maybe we'll start with some spanning forests. Yes, that's the order of the slides. So again, I will go over this quickly since Asaf discussed this in much greater depth yesterday. But if you have a finite graph, you can easily take a finite spanning forest, a finite spanning tree to be precise. So you take uniformly one of the trees spanning. This is a finite subset of the grid. And you can take a limit. If you have an infinite graph, you can exhaust it by finite graphs. Take a finite finite spanning tree of each of them and take the limit of the configuration of edges that you see. This limit converges. This appeared in the case of the lattice. This was also central to Martin's talk. And so, so this is what you see in the case of a finite part of the grid. And there are two spanning forests, actually. There's the free and the wired uniform spanning forest. So the wired uniform spanning forest, what I took here is a part of a grid, but I identified all vertices outside to a single vertex. So you should think of this red square as just one big vertex that's drawn not as a dot, but then we have some grid inside it, and we took a uniform grid, a uniform spanning forest of the red lattice. And for this, again, you can just ignore the black lattice, and we have here a uniform spanning tree in a finite part of the grid lattice. And again, you can take these two objects and take a limit. So in the case of the black one, you get the free uniform spanning forest. And in the case of the red one, you get the wired uniform spanning forest. And again, this construction makes sense for any graph. In planar graphs, you have this duality. So you get that the wired uniform spanning forest is the dual of the free uniform spanning forest in this sense. So if you have a planar map, so if you have a planar map and you have some subgraph of the planar map, which is the forest, then you have the subgraph of the dual map, which includes the dual of every edge that is not in the forest that you took, or in the tree. So we have here a spanning forest. Well, it's almost a forest, almost a tree. So we have here a spanning tree in blue and the dual spanning tree in red. So this construction makes sense only in the planar case, and it gives a connection between the free spanning forest on the map and the wired spanning forest on the dual. So so this is the, and okay, we'll come to this a bit more in a bit. So again, this is a larger picture of the wired and free uniform spanning forests that you also saw in a substock. This is on a segment in the square lattice. You can also ask, what does this look like in the hyperbolic case? So this is a picture due to Russ Lyons of a hyperbolic planar map. So this is just a periodic lattice in the hyperbolic plane. The black graph is a lattice, the red graph is the dual lattice. And you can also take a spanning forest on that. So we have here, so what we have here in this graph, we have in blue we have a, so I think in blue it's the free uniform spanning forests on the lattice, on what is the black lattice here. And in red we have the dual spanning forest, which is the wired uniform spanning forest on the dual. Now, one of the questions that came up in Asaf's talk, and the main result that Asaf discussed indeed, is about the connectivity properties of this. And again, if you have very good eyes, you might recognize that in this case, the blue one, the free forests on the map, is connected. And this is actually a special case of Asaf's theorem, because this graph has bounded degrees. So we can see from Asaf's theorem that this is connected. The red one is disconnected. So the red one has infinitely many connected components. This is the wired spanning forests on the dual map. Okay, so we have these two cases. We have the parabolic case. We have a forest and the dual forest. We have the hyperbolic case with the free forest and the dual wired forest. And there are a couple of facts that I would use now. So the first of all is that is a special case of what you see there. If you take any spanning tree in a map, in a planar map, then you have the dual tree. And if you take a free forest on the dual map, this is the dual of the wired forest on the map. And if you take the free forest on the map, it's the dual of the wired forest on the dual map. So going between a map and its dual, you switch between a free forest and a wired forest. So that's one comment. A second comment is that the free forest stochastically dominates the wired forest. This is true on any graph. So it's possible to have a coupling, and it was mentioned briefly by Asaf. It's possible to have a coupling of the wired and free forests so that the free forest is a superset of the wired forest. It contains every edge of the wired forest and possibly some additional edges. And if you go back to here, you see that one of these squares is the identification of the wired and free uniform spanning forests. So we would like to know whether they are equal or not. And in fact, I will show you now that in the parabolic case, when you have zero average curvature, they are equal. And one final basic fact that you need to know is that if you have a unimodular graph, the wired uniform spanning forest has degree 2, average degree 2. So could you raise the projector? Could you shut the projector for a minute? Or more? Is there anyone who could shut the projector and raise the screen?
The answer is no, Omer.
Thank you. So, okay, so I want to show you that the wired and free uniform spanning forests are equal when you have zero curvature. And the basic idea is the following. So we know that the wired uniform spanning forest is a subset of the free uniform spanning forest. So let's just call this W and let's call this F. So the wired forest is a subset of the free forest. Now I claim that the wired forest has degree 2, has average degree 2. And the reason for that, you can see this actually by a fairly simple mass transport principle. Okay, well, you need to, so if you know Wilson's algorithm, to be precise, so there is a construction of the wired spanning forest which is one-ended. So you have a single infinite path. You can show from this that the wired uniform spanning forest is going to be one-ended. So every component is one-ended. And you can get an oriented version where all of the edges are oriented towards infinity. So from every vertex, you have a unique edge going out. And now we can apply a very simple mass transport where every vertex sends one unit of mass along this the edge towards infinity. And in fact, you don't even need that it's one-ended for this. You just need that there is an oriented version of the forest that is constructed by Wilson's algorithm. So every vertex sends out a single unit of mass along the edge directed out of it, but the whole thing is unimodular. And therefore, every vertex also receives on average. So a random vertex receives on average one unit. So on average, you have one edge going in. So you have on average one edge going in and exactly one edge going out, so the average degree is 2. Do people buy this argument? Yes, it seems yes, but there is actually one crucial point here that is missing. I said that if you have a map, then the wired forest on the map is unimodular, if you have a unimodular map. But it's not the same graph. So you started with a map, and we now constructed some subgraph of it, which we claim is unimodular, and it's not true that the subgraph of a unimodular graph is unimodular generically. However, it is, and the main idea, the main intuition that you should have is that if you take any unimodular graph and you apply some transformation to it, in a way which is local and respects the symmetries of the graph, then the resulting graph is also unimodular. So if you take this random graph and you do random walks on it, so you can certainly take random walks on the graph, and you can do loop erasure and run Wilson's algorithm. So you can do this, and you can deduce that the result of Wilson's algorithm on any unimodular map has to be unimodular. This is true not just for things like the wide spanning forest. It's also true for going between a map and its dual. So if you have a map, so let me make a claim at this point. So a map is unimodular if and only if the dual map is unimodular. And there is some issue here, because it's not clear how do you choose the root in the dual map. So if you have a random map so to be more precise, you have here a map with a random root rho, which is a unimodular. So what is the random root in the dual graph? So there is something here to be done, and this follows from this has been done by Aldos and Lyons in 2007 in the 2007 paper. But okay, but now if we have a unimodular map, then also the dual of the map is unimodular, and on either one of them the wired uniform spanning forest is unimodular and has degree 2. Now the free uniform spanning forest we know is a superset of the wired uniform spanning forest. So if we want to show that they are equal, we need to show that the degree in the free forest is 2. So what do we need? We need, if the expected curvature at the root rho is 0, then the expected of the degree in the free spanning forests of the root rho is equal to 2. Since then you have the two forests, they have the same expected degree, one contained in the other, so they are equal. And this follows from the following claim. The expected degree in the free forests of the degree of the root in the free forest is equal to 2 minus the expected curvature of the root rho.
You need to divide by pi. No.
Yes. Thank you. So this is and this actually is a fairly straightforward consequence of understanding the connection between the map and the dual map. But in order to see this, we need to first of all say something about mass transfers between the map and the dual map, about the connection between the map and the dual map. So suppose you have a map, say the triangular lattice. So if you take the triangular lattice and you have the dual map, which is a portion of the hexagonal lattice, and then you have the double or derived map, which is what happens if you superimpose both of them. So you have here, lots of vertices, but you also have vertices where the edges cross. So all of these constructions being sort of local constructions, which you just get from the graph. So all of them are going to preserve unimodularity. But you have to be a bit careful, because the intuition of a unimodular map is one where the vertex is chosen uniformly at random. And in this map, you can see that you don't have the same number of white vertices as red vertices. Since for each white vertex you have 6 red vertices, for each red vertex you have 3 white vertices. So you have twice as many, in a given area you have twice as many red vertices. So actually you want to, so if you want to choose a random root in this map to make it unimodular, then it's not that you choose with probability half a white vertex and half a red vertex, or 1/3 white, 1/3 red, 1/3 green, but you should choose this according to the relative frequencies. And so there is a version of the mass transfer principle which allows us to work on this extended map. And what this says is that if you have so for a mass transfer from the map to the dual map, so if you send mass from the map to the dual map, you get some prefactor. So the expectation of the sum of f of g rho x x in the dual map is equal to some constant times the expected sum of f of g x rho. Or let's put a rho star here, since this is the root of the dual map. And this should be expectation for the dual map. So this constant q is corresponds to the ratio of the number of vertices in the map and the number of vertices in the dual map, essentially. So in this case, you have twice as many vertices in the dual map, so q will be a half. And maybe one more comment about this, that there is a way to eliminate this constant if instead of looking at a uniform root vertex, you look at a uniform root edge. So whenever you have a unimodular map, you can bias it by the degree of the root vertex. So you get a new measure, which is, so you just bias it by the degree of the vertex, so vertices with high degree are more likely. And this measure, and once you do this, you can choose you should think of it as every edge being equally likely. So you have a map where every edge is equally likely to be the root. And edges of the map are in bijection with edges of the dual map. So that's a canonical bijection. For each edge you have the dual edge. And so you can deduce that, so you don't need this constant there. Well, okay, so just to finish the argument here, once you know this, it's very simple, because you know that well, okay, so I won't write the computation, but basically the expected degree of so if you have the free forest, so if you have the free spanning forest of the map, you want to know what is the expected degree, so you need to know what is the probability that a particular edge is contained in the map. This is 1 minus the probability that the dual edge is not in the dual forest. But the dual forest is the wired forest. So we know that around the typical map, around the typical vertex, the expected number of dual edges that are in the wired forest is 2. So on average, you have 2 edges here. So for example, in this case, on average, you have 2 edges in the dual red forest, which tells you what is the probability of an edge being in the horizontal forest. It will be 1/3 in this case. And if it's 1/3, then in this case you have degree 6, so the average degree is 2. So this computation works also in the general case and gives that the wired and free uniform spanning forests are the same. Okay, so I have 5 minutes. Yeah. So. Okay, so maybe I should say, so let me not talk about some of the other implications, and let me say a little bit about the conformal type, since this is one particularly nice property of these maps. So the conformal type of a map, so as I discussed, so if you take the map and you take some polygons and glue them to get a surface, so you actually have a Riemann surface. And by the Riemann uniformization theorem, it's conformally equivalent either to the plane or to the hyperbolic plane. Either to the plane or to the disk. And this is the conformal type. So we want to know whether it's conformally equivalent to the plane or to the disk. So in the case of the UIPT, for example, it was proved by Rode and Gill that it's conformally equivalent to the plane some time ago. And we claim that when you have average curvature 0, this is equivalent to being conformally equivalent to the plane. And the argument is again a very natural mass transport argument. And let's consider it in the hyperbolic case. So let's suppose that we have a map which is conformally equivalent to where the surface is conformally equivalent to the hyperbolic plane. So we have some map which is now drawn in the hyperbolic plane. Something like that. And here's a mass transport that I'm going to describe. So the mass transport from a vertex x to y star. So if we have some vertex x and we have some face, so let's just call it f. So we have a face f, and the amount of mass that x sends to the face f is just going to be the angle, the angle of the face f at x. So that's the mass transport, and we're going to analyze it. So the expected mass out of every vertex is 2 pi. Since the total angles, you'll agree, the sum of these angles is 2 pi. So that's not a problem. So now I want to know what is the expected mass flowing into an edge, into a face. What's that? So the expected mass in, so we can apply so we have a formula for that. So it's equal to pi times the degree of the face minus 2 pi. So that's the first term. But then we have a term corresponding to curvature. So if you have curved faces like that, then they receive more, which comes from the curvature along the boundary. So we have the integral around the face of the just curvature of the arc with respect to arc length minus the area of the face. So this is all in the hyperbolic plane. So in the hyperbolic plane, you have some curvature for the surface itself, so you need to take this into account. If you work in the parabolic case, then you don't have this term because it's flat. So we have, this is the expected mass in, and we get that that the expectation of this is known to us. So it's not exactly 2 pi because we have this prefactor q there. But we know what this is. Now we have this term here, the integral of the curvature. And for this, I claim that the expectation of this is 0. And you get this because you can just say, you can apply some simple mass transform just on the dual map, where every face sends to the adjacent face the curvature on this edge. So the total mass sent out is the total curvature. And the total mass get in is the negative of the curvature because it's from the other side. And so you get that this has expectation 0. So this has expectation 0. Let's remove it. And from this, you just do a simple manipulation, take into account this factor q, which I will not write out in detail, but what you get is exactly that the expected area is that the area is exactly proportional to the curvature. So, so the summary of this is that the expected area of a face is equal to the expected curvature, or negative. Maybe with the 1 over pi. Is there 1 over? No, it shouldn't be 1 over pi here. Yeah, so the expected area is just a curvature. So if you have negative curvature, so if you have positive area, then you get negative curvature. So in the hyperbolic case, you get negative curvature. In the parabolic case, as I said, this term is missing, since this term is actually the integral over the face of the curvature of the surface, which is flat, so you get 0. So that shows the conformal type is equivalent to having 0 curvature. Okay, so let's see. Do we reach this or?
Omer,
Yeah.
can I ask a question? So when you ignore the integral of the curvature, don't you have to make an assumption on the degree to say that it's finite? Something like that.
Yes, so this proof is actually false. So indeed, this is one problem with this proof. I guess we're into the questions now.
Yeah.
Yes. So this proof is actually false precisely because of this. We don't have any a priori argument to show that this is integrable. And for to apply the mass transport, you need things to be integrable. So there is a variation of this proof that does work. So the result is still true. But at the moment, our argument is based on modifying the map. So you have the vertices, but you replace instead of having these curves, you replace them by some other graph on the same vertices. Basically, the low-limit regulation, but you have many choices. And the crucial point is that making some changes to the graph, like replacing some edge by a different edge, doesn't change the average curvature. So if you cut some faces by adding edges and remove other edges, this only moves curvature around. It doesn't change the average curvature. So we can justify this and switch to this other graph. And for this other graph, we don't have this problem. So, but yeah, that's this proof is not quite complete as shown. Thank you. And other questions?
So let's thank the speaker again.